So I am going to introduce you the chemical potential, and I am going to use this symbol, chemical potential, as mu A. And you remember the partial molar Gibbs free energy. So what that means is how much of the Gibbs free energy is increased when you add compound A by 1 mole, keeping the other term constant, temperature, pressure, and other, like a B, C, D, F, G, so other terms constant. So that's the definition of chemical potential. And now it becomes the DG equation, what you used to know, VdP minus SdT. That's for the pure compound. So now we have onto this, you need to multiply chemical potential of A, chemical potential of B. So you are, by adding A and B to the system, you are increasing the Gibbs free energy. And not only how the total volume, pressure, and temperature is defined, and this is how they are going to affect the overall Gibbs free energy. And you know, when at pressure is constant and temperature is constant, isothermal, and you start to see the awfully similar, which is a dG is a mu A, B and A, mu B, B and D. Looks like a partial molar volume scenario. I'm just writing this way. Yes, it is the same thing. So once again, the G is nothing but mu A Na, mu B, NB. Just the same logic. You do the integration for a mixture from 0 to final Gibbs free energy by adding components A and components B to the final destination, keeping the ratio same. So I got these two together. And naturally, the equation that is coming up by taking the total G again, and then you will have Na, D, mu A, Nb, D, mu B is 0. Okay. So once again, this is, right? It's the same drill. If you do the dG, there will be mu dA minus dNA plus d mu A times Na. And if you subtract from the top to bottom, this is all first term gone. The remaining term is this one. Do the same thing. This one is d mu B NB times mu B dNB. And if you subtract from the bottom, second term is gone. This is term with surviving. And so therefore, the same thing, d mu A, d mu B is minus Na and B, and it's called a Gibbs. Anything with a name on it has a very important landmark equation, and this is one of them. This one is, instead of being very practical, it is more philosophically important one. In the mixtures of A and B, you cannot change the chemical potential in the mixture without changing the other chemical potential. They are interrelated each other, and that's all I'm saying. I mean, this is can be used that in a practical sense is not so much, and that's what the chemical potential, they are interrelated each other, and that's the so this was actually part of the A1, which is A1 was a partial molar quantity. Now the thermodynamics of mixing, which is A2. believe it or not, I still do research on thermodynamics of mixing. This has something to do with phase separation and how things are miscible, non-miscible. It has a lot of implication on this. And the system that, the easiest system that they do is number A. A is gas mixtures. Okay, so I mean, nobody's doing the probably mixing of gases. Do you know when you mix the gas, are they miscible? The gases, have you seen the gas do not mix? If you have a nitrogen, oxygen, hydrogen, do you see that they remain as a separate gases? Never, right? Gas is always miscible, and my job is trying to show you that why gas is always miscible. And the answer is always mixing is a spontaneous process. So the goal here is what is called the delta G mix. Okay? I like to write this way, but this textbook like to write delta mix G. I mean, we are talking about same thing here. Okay? We want to do that, and then this one, I want it to be negative. And that means the mixing is a spontaneous process. There are more complicated story that I will talk about in my graduate course, but this is what is coming down to these cases. So I want to do the recap. Okay, remember how many times did I write this equation? A lot of times, right? So I'm going to pick on this. Okay, I am going to say temperature is constant, so this is isothermal, constant temperature. So I'm going to deal with this here. And what I'm going to say here is, I'm going to change this, dgm, so dm dp. And this seems to be a lot simpler to understand before. And this one now, I'm going to say that will be a P and RT. So it's a RT dP. It's a dP. So no trouble getting to this part, right? Just say, all I'm asking is, let's just assume this is an ideal gas, and I can use this equation. And once I have that, this is a dP over P, which is a natural law, and this is an RT. So what I'm doing now is, I'm going to do the integration of dgm. That will be a RT integration of P dP. You see that? You see that? Where you're starting from? I guess my starting point is something what I call Gibbs free energy at the standard state. And the Gibbs free energy at any pressure. So my starting pressure is pressure with a bar. This is a 1 bar, reference pressure. And this is the pressure. This is the one that, so therefore I'm getting this equation. Gm at pressure P is a Gm, this one, plus RT natural log P over P. Okay. And I am going to delete that, okay? So it's just I'm trying to show the pressure dependence, and my reference is this. So this is, you know what's the pressure? This is a 1 bar. That's a standard pressure, so that's the equation. Somebody can write this equation too. You probably have seen this equation writing this way if you're looking at Other textbook. People just write this.
Okay, I'm gonna catch you in like 5 minutes.
When you see an equation looks like that, I always go and looking at the unit matching. What's the unit? Energy. Energy. Okay, that's an energy. What? Natural P? This cannot be real, right? But they want to, this is a real, okay? This is a real, this is a one. But sometimes the people just write it, this is a short form. And what they imply is P is always in the unit of bar. Okay, they write it, this equation works like a charm. So they use this equation as well. Okay. And then what am I saying now is how about that? Do you see that this one coming? Because you remember mu is n. So I'm just making a mu as a general. Okay. Well, I cannot do that, so I guess I have to put an A there. Okay. We'll put an A there. So maybe I should put an A there. Compound A. And that's an equation that I can come up. Because this is the molar Gibbs free energy on the temperature, pressure constant, and B. And this is an equation that I can use. And why this is important is because I'm going to get this kind of this is a very limited cases, but the derivation is much easier to understand. So let me show you this. I have this closed container with a valve in here, and you have an Na, you have an Nb. Okay, and then the pressure here is P. Pressure here is a P. This is a very boring experiment. Okay, I have a container, right? Two containers, same pressure. One is nitrogen, the other is an oxygen. Okay, and I maybe 10 moles here, 100 moles the other side, but I have a pressure is the same. I want it to be this way because that makes my life easy. And then what I'm going to say is this is an initial. Your final state.
I don't know.
I gotta close this thing. There you go. We're almost there, right? So, okay. So look at that. So I'm going to open it up. And the A will diffuse in and out. B will diffuse in and out. The key point is, what's my final pressure? It was a 1 atmospheric pressure, 1 atmospheric pressure, right? I open it up. What's my final pressure in this? 1. It doesn't change, right? So if the total pressure is the same. But now look at what happened here. Now the A moves the other side, B moves the other side. Everything is homogeneously mixed it in. Right? So what's my pressure here? As far as A is concerned, you experience partial pressure of A. Right? And do you remember partial pressure of A is XAP total pressure, which is the same as your original pressure. So what I'm saying here is that this is also good to know. I'm an A. I used to exercise the pressure P. Well, I feel the pressure P. Now I only exercise the pressure PA. As far as A is concerned, now I have a bigger playground to move around. So effective pressure, the partial pressure for A is small. Right? Does it make sense? Make sense? No? Yeah? Okay. What about B? So it looks like there's nothing happens, right? I only thing that open that up is A moves around, B moves around. There's no like a pressure differences. Same pressure before and after the total pressure. But the partial pressure, as far as A is concerned, I don't feel the same. If B is concerned, I don't feel the same. And the total pressure is now additional partial pressure. Okay. So you guys remember now, chemical potential for gases is a pressure they are feeling. It used to be a large pressure, now only a partial pressure. So it used to be 1 atmosphere pressure on both sides. Now you mix it in, they exercise only half of the pressure, half pressure and other half pressure. So your effective pressure, this one came down. So chemical potential is coming down. I can be as naive as that, okay? This is naturally happening this way. The exact equation for that is I'm going to derive it, I guess, next class. Okay? So yeah, well, too much information today. But we come up a long way. Now the chapter 5 is a mixing, and this is something that we're going to talk about for some time.